Hello, this video goes through problem 4.7 worked out. Problem 4.7 asks you to determine the surface level moment capacity. And this is at either FC, a compression stress not to exceed 0.45 F prime C, and your steel stress can't exceed 30 KSI. So what we need to do is determine what stress distribution is this at. And until you get used to looking at these values, you need to look at what these values mean. So determine what stage this corresponds to. We want to check and see have we cracked and are we elastic, and that'll tell us what stage we're at. So we know from the previous problem 4.2 that our rupture stress is equal to 7.5 square root F prime C, and F prime C is in PSI. This comes out to be 530 PSI. So anything above this means that we've cracked. So at this stage, if we have a concrete stress of 0.45 F prime C, we're at 2200 PSI. So we're definitely beyond the cracking stress. So we have definitely cracked in this section. And with our steel at 30 KSI, we're still below the yield stress. So we're still in the elastic region. So we have a crack section and we're in the elastic range. So this means we're in stage 2. So stage 2, we need to look at a stress distribution that looks like this guy down here. But how do we find what this KD is? What we need to do is look at the geometry to find the neutral axis. What we'll take is the concrete and compression, and then neglect all of the concrete and tension because it's cracked, so it's not giving us any strength at this point. So the effective depth then is the distance to the steel from the extreme compression fiber, and previously this is left over from problem 4.2. And then our cross section is still B. We're going to use our transformed steel for this, and it's going to be balanced by a fraction of the effective depth, and that fraction is going to be denoted by this K value. So to find this K value, we just sum the moments of the areas about the neutral axis. So these moments of these areas are equal to, the area is KD times B, that's our area, and then the moment arm about this neutral axis, this unknown located neutral axis, is KD divided by 2, and then the distance to the neutral axis, or from the neutral axis to the steel, is D minus KD. So it's this distance that we're looking at is the D minus KD, and the force is the N, or the area, I'm sorry, is equal to the N times AS, and N is our modular ratio, which is the ES over EC, and from problem 4.2 that was 7.2. So you plug in also, you know your reinforcement ratio is equal to the area of steel in the section over the effective area of the section. This comes out to 0.00632. We plug this into our area of steel for this equation so that all we have, our only unknown is K for this equation. So we can solve for K. We rearrange all this and get this quadratic equation and solve for K to be 0.259. So this means that our compressive stress is distributed over a section that's about 25% of the depth, the effective depth of the section. So all of that concrete, and then it's distributed in a triangular manner. So that means that this depth, KD, is resulted by is a stress distribution of triangular shape over this KD and then over the width of the section as well. And it is balanced by a single stress vector located at the centroid of the steel. Okay, so looking at the distribution, and to get the resultant of this distribution is we take the area of the section, or basically the volume of the section, and we apply it at 1/3 from the top or 2/3 from the 0 point. Our C is just equal to 1/2. The base, I like to look at the triangle of this, the base of the triangle is KD the height of the triangle is FC, and then the volume is gives you this distance back out of the page. And then because it's a triangle, the area we divide by 1/2 or multiply by 1/2. So this gives us our resultant. And then our tension force, T, is just equal to the steel stress times the area of steel. The problem's asking for the service level moment capacity if the steel stress is less, not to exceed 0.45 F prime C, and the steel stress cannot exceed 30 KSI. So we take the sum of the moments about each resultant, and the maximum moment is going to satisfy, and the maximum moment that satisfies FC less than 45% F prime C and Fs equal to 30 KSI. So doing that, our effective depth is equal to the full section height minus the distance to the reinforcement from the tension fiber. We have an effective depth of 33.5, multiplying that by the 0.259 K value that we had, dividing that by 3, that gives us our moment arm from the extreme compression fiber for our resultant compressive force. So if we do the moment about the concrete resultant at this point, that is equal to our Fs times As, that's our force, and then our moment arm is D minus KD over 3. This comes out to be 2,300 kip inches. If we take the sum of the moments about the steel resultant, we end up with, this is our force, our compression resultant, times the same moment arm. That comes out to be 3,600 kip inches. So in order to satisfy both of those compressive, those concrete limits, the stress limits, we need to take the minimum moment capacity. So the minimum moment capacity here is the one that's controlled by the steel limit, and it is equal to 2,300 kip inches.